Average velocity. Velocity is a vector quantity. It describes how quickly an object's position changes and the direction of the change. It's measured in meters per second. Speed sounds very similar to velocity, but it's a scalar quantity. It only measures the magnitude of the velocity. It doesn't tell you which direction an object is moving, but it's still measured in meters per second. Let's think about an escalator going up and an escalator moving down. Let's say they're both moving at the same rate and they're both moving the same distance. So let's say they move 10 meters each, but this one is moving up and this one is moving down. So we'll give the direction here. 10 meters up versus 10 meters down. They have the same speed, but they do have a different velocity because they're moving in different directions. How do you determine velocity on a position time graph? Well, it's determined using slope. Slope equals the rise over the run. To figure out the average velocity, we'd figure out the change in displacement divided by the change in time. Average velocity is the rate of change of position over a time interval. We use average velocity because in reality slight changes in speed occur because of uneven surfaces or wind or other factors, and we wouldn't get a straight line graph where all the points connect. If we use average velocity, we can have a nice straight line graph that shows the relationship. Let's take a look at an example of how this works. On this position time graph, we'll plot position over here, and remember that's measured, that's shown like this. And time, almost without exception, always goes on the x-axis and is usually measured in seconds or hours. Okay, so let's say this is time 0 and position 0, or the position that is the point of reference. If we have an upward slope, we say that the object is moving away from the origin. And since it's moving away from the origin, we call it positive slope. So let's say an object moves away from the origin and then it comes to a rest for a period of time. And then suppose it starts moving back to the origin. As it moves back to the origin, we could say that it has a negative slope. If we label each part of this graph, we might be able to think of a scenario where something like this occurs. We could think of the origin as school. Let's say we're taking a field trip and we're taking a bus on this field trip. During time period A, the school bus is moving away from school. And let's say we're going to the aquarium and we stop there at the aquarium for a period of time. That's where B is. The bus is stationary, it's not moving. And so its position isn't changing. And then it's time to go home. We all hop back on the bus at the aquarium and it starts moving back to the school. That would be C. So we can use a position time graph to plot our trip. Sometimes we want to be able to calculate average velocity. This is the formula we use for that. Average velocity equals change in displacement divided by the change in time. Let's look at a scenario where this might be used. Let's say you decide to go for a brisk walk. In a hurry, you want to go about 75 meters forward, and you do this in about 8.25 seconds. Let's just say 8.2 seconds. So we want to find out what the average velocity is for this person, who actually isn't probably brisk walking, but is probably actually a sprint. So we look back at our formula and we say, okay, the average velocity, because maybe sometimes they're running faster, sometimes they're running slower. The main thing we know is that it took them 8.2 seconds to travel 75 meters. So we put that into the formula, and the change in displacement is 75 meters forward divided by the change in time, which was 8.2 seconds, the time it took that person to travel that distance. And what we should get is plus 9.1 meters per second, which gives us the average velocity the person was traveling at in a forward direction. And the way we know that it's forward is because of this positive sign. And if you recall, we kind of give these directions some positive and negative kind of values. So if you're moving forward, it's positive. If you're moving backward, it's negative. Left is negative. Right is positive. North is positive, as is east, and south is negative, as is west. We've just kind of decided that that's how we're going to think of these things in mathematical terms so that we can tell which way the direction is, and it's agreed upon. You kind of just have to remember them. So let's take a look at how we could rearrange this formula if we were given two other values. In the example we just looked at, we were given the displacement and the time, and we had to calculate the velocity. But let's say we were given the velocity and the time, and we had to calculate the displacement. Well, in that case, you just rearrange the formula, and you come up with change in displacement equals average velocity times the change in time. And let's say we were given displacement and velocity but not time, and that was what we needed to figure out. We'd use this formula: delta D, displacement, divided by the average velocity. We can always figure out one value if we have the other two values. With the original formula, we can figure out velocity. With this one, we can figure out displacement, and with this one, we can figure out time. So you should either memorize those formulas or know how to manipulate the original formula to get the displacement variation of the formula and the time variation of the formula. You should go ahead and work on your workbook and check your understanding at the end of this section, and even try some problems in the chapter review. This is just the theory. You actually need to try the problems to really understand this.